Okay, recall there's a difference between speed and velocity. So speed is a scalar quantity, and velocity is a vector quantity. So for example, if I told you that this morning I was driving my car at 25 meters per second, then all you know is how fast I was traveling. I only gave you scalar information. If I told you I drove my car at 25 meters per second at an angle of 30 degrees north of west, okay, then you can get a better picture of exactly how I was driving my car. In fact, we could represent a velocity of that sort by displaying it as an arrow that represents the vector on the unit circle. Let's see. North is associated with the positive y-axis, south with the negative y-axis, east with the positive x-axis, and west with the negative x-axis. So to go 30 degrees north of west, I guess that means you're not pointing exactly due west. This would be a vector that points a little north of west. Now, by the way, if this is 30 degrees, then we know this angle, measured off the positive x-axis, will be what? 150 degrees, correct? So I think it's probably pretty good convention to stick to always measure your angles going in a counterclockwise direction relative to the positive x-axis. So another way to give this same description of the vector would be to say I traveled at 25 meters per second at an angle of 150 degrees. So when it's not stated clearly 150 degrees relative to what, it can be assumed counterclockwise relative to the positive x-axis. You know, equivalently, we could say, oh goodness, not to confuse you, but to throw another angle in here, I guess this right here would be 60 degrees, right? So 30 degrees north of west is the same thing as 60 degrees west of north. But if you don't state things like this, west of north or north of west, then you can just state an angle and it's implied relative to the positive x-axis. Okay, so that's one option for vector notation, is to state a magnitude and a direction. And when we represent that vector graphically, the magnitude is nothing more than the length of that vector. So if I increase my speed from 25 meters per second to 40 meters per second, well then I just simply have to draw a longer vector, but still pointing in the same direction if the only change I made was in the speed. Okay, so yeah, for sure. The length of the vector is a great way of representing its magnitude, and direction speaks for itself, since there is indeed an arrowhead on all of these vector representations. The other option is what's known as unit vector notation, and I believe I covered this briefly in a previous lesson. If we zoom in, we can see that this vector points somewhat westward and somewhat northward. So I can represent the westward component of this vector. See, if I drop a line straight down to the x-axis, then this appears something like, it's as if there's a shadow of the vector lying along the x-axis. And likewise, we could project something like a shadow onto the y-axis. Okay, so what we're looking at are the two components to this vector. So if we draw this again, just to be clear, you have your y-axis and your x-axis, a vector whose length is meant to represent a speed of 25 meters per second, and is directed off of the positive x-axis at an angle of 150 degrees, has two components to it. One that lies exclusively along the x-axis, and a second component that lies exclusively along the y-axis. So if we're labeling this vector v because it represents a velocity, then we can call this v subscript x for the horizontal component and v subscript y for the vertical component. But you see that these components help form a right triangle. And so if we reproduce, let's say, for example, the vertical component, notice I have not rotated or stretched this vector when I draw it again over here, so it's still the same vector. Then we have a right triangle. It's kind of hard to miss, right? Right there, clearly indicated and highlighted here in yellow, is a right triangle whose hypotenuse and base and height are clearly labeled. Now we'd get the same thing if we reproduced the horizontal component to the vector, right? I'm going to draw a vector of the same length and pointing in the same direction as this vector. And so then we can highlight maybe in orange the same triangle. Okay, so let's apply the idea that the sine of an angle is equal to opposite over hypotenuse, and the cosine of an angle is equal to an adjacent side over the hypotenuse. So if we're looking at this angle right here, that was the 30 degrees that was originally given in this statement. Then we can use these expressions and say the sine of 30 degrees, or we can keep it generic and just call it theta, would have to be equal to whatever is opposite that angle, v subscript y, divided by the hypotenuse, which is the overall velocity itself. When we cross multiply, we find that the vertical component is v sine theta. This is very much the same approach we were doing when breaking velocity vectors into components in our study of projectile motion. Okay, so likewise, the cosine of this angle is equal to vx over v, and we cross multiply, and we find that the horizontal component is equal to v cosine theta. However, we have to be careful here. Notice that the vertical component indeed points along the positive y-axis, but this horizontal component points along the negative x-axis. But if you were to take the cosine of 30 degrees, you would get a positive result. However, if we use an angle of 150 degrees instead, then the horizontal component will definitely come out as a negative value. Let me illustrate that with the numbers that were given. So if we said Vx is equal to V cosine theta, 25 meters per second times the cosine of 30 degrees, you grab a calculator and see what you get. So that would give you about 21.65 meters per second. But if we did 25 meters per second times the cosine of the supplementary angle of 150 degrees, which is the angle measured off of the positive x-axis, then we would get a result of negative 21.65 meters per second. Now, by the way, if we find the vertical component, it's 25 meters per second times the sine. Well, let's try option 1 and option 2. Let's try 30 degrees, and let's try 150 degrees. Well, the sine of 30 degrees is, you know that one, that's a special angle, that's 1/2. So this would give you positive 12.5 meters per second. What do you get when you use 150 degrees? Try it on your calculator. Take the sine of 150 degrees and multiply that by 25, and lo and behold, that also gives you positive 12.5 meters per second. And we certainly hope that we get a positive result because we can see graphically that that vertical component does point in the positive direction. So the bottom line, what I'm trying to get at is we should always use the angle measured off of the positive x-axis as a way to find the components, because then it'll truly give you the correct result, whether the component points in the positive or negative direction. So option number one, it's not so bad. It gave us the correct magnitudes, but you would have to think your way through how you're going to label the results as being positive or negative. But if you always strictly stick to an expression of angle as measured off the positive x-axis, it takes care of the sign for you. Well, a vector that's exactly 1 unit long, instead of 25 units long, if you have a vector that's precisely 1 unit in length, pointing along the positive x-axis, that vector is known as I hat. So I guess that means if you had a vector that's exactly 1 unit long, pointing along the negative x-axis, then that would be a vector known as negative I hat. And in the same way, a vector that's 1 unit long, pointing straight up along the y-axis, is named j hat. So what if I have a vector, maybe it's, well, let's say on a different day I drive 25 meters per second, but I drive that 25 meters per second, instead of at an angle of 30 degrees north of west, what if I drive due east at 25 meters per second? Well, I could reproduce this vector that's 25 units long just by stringing together 25 of these vectors known as I hat, end to end to end to end to end. And so this vector could just be stated as 25 multiplied by I hat. And in the same regard, if I were to drive at 25 meters per second due west, then I'd string together 25 negative I hats. So negative 25 times I hat. So the question we have is, how could I represent the vector that corresponds to a velocity of 25 meters per second directed at 30 degrees north of west? Well, since that's the same thing as 150 degrees off the x-axis, we use these formulas to find the components. So we have a component strictly along the x-axis, and we have a component strictly along the y-axis. And it looks like this component along the x-axis can be reproduced by stringing together a certain multiple of negative I hat. Now, what multiple is that? 21.65. So in part, this vector v, which was originally stated as 25 meters per second at an angle of 150 degrees, could alternatively be stated as negative 21.65 of I hat combined with, well, how many multiples of j hat do I have to string together? 12 and a half. So if I add with this 12 and a half j hats, this is a way of giving me the same information. So this is what's meant by putting a vector in unit vector notation as opposed to stating a magnitude along with a direction. Just two ways of saying the same thing. And we'll be able to apply unit vector notation rather easily when we move on into our next lesson of how to add velocity vectors using the Galilean transformation in 2 dimensions. So stay tuned for more.